Okay, continuing with the second half of chapter 24, which is the complex numbers in the electrical circuit. Let's look at the complex number and its use of it in a series AC circuit. So let's say we have a series circuit with resistors and the reactances in this case. So we add up all the resistances, which are the real part, and all the reactances. In this case we have X of L which is positive for J and X of C with negative 12J, and so we add those up, so we end up with 6 minus 8J or J8, which is the total impedance of the circuit. However, this is in a rectangular form. We want to convert this into the polar form and then divide the total voltage by this impedance to get the current. Of course, the current is the same in the series circuit. So next, we convert the circuit into its AC complex representations, and then when we find out the total impedance, convert that into the polar form, which we talked about in the last section. And the total current is nothing more than the total voltage, which is 20 volt with 0 degrees angle, divided by the total impedance in this case, which is 10 with the angle of minus 53. So when you divide the two polar form here, at the bottom here to the left, you divide the coefficient, which is 20 divided by 10, which gives you 2, and you subtract the angle in the denominator from the angle in the numerator, so it gives you positive 35 degrees. So the current in this series circuit using the complex number come out to be 2 amps with the angle of 53 degrees leading the total voltage. So if you look at it graphically, this is the total voltage and my current is leading that voltage by 53 degrees. Now of course the voltage of the resistor is going to be on the same line because the current and voltage in the resistor do not change phase with each other, so they are going to be at 53 degrees. And for the capacitor, you know the capacitor voltage lags the current by 90 degrees, so if you go 90 degrees gives you where the voltage of the capacitor is going to be. It's basically going to be 12 times 2, which is 24 volts, but the angle is negative at 37 degrees. And for the inductor, we know the value is 4 times 2, 8 volts at the angle of positive, because for the inductor the voltage leads the current by 90 degrees, so it's going to have the angle of 143 degrees. Another useful application of the complex number is converting a parallel circuit into an equivalent series circuit. For instance, if you have a 10 ohm inductive reactance in parallel with the 10 ohm resistor, well, in this case, in a complex notation, you know that the R is basically 10 plus the coefficient for J is 0, and X of L is with the no real part and coefficient of J is 10. So you multiply the two and divide by the sum, which is the power combination of two impedances in parallel, and in polar form it comes out to be 7 for the amplitude and 45 degrees angle. As you can see, these two impedances are exactly the same if you work out the complex numbers. Suppose you have two branches with the complex numbers in it, one with the inductive reactance and the other one with the capacitive reactance. Then you get the individual branch series resistances and capacitances, and then you do the impedances, and then you use the equivalent resistance, which for the parallel circuit, the product over the sum. We do the same thing here, except instead of resistances we have impedances. So let's look at this example. We have two branches One branch consists of a resistor in series with the inductor, and so we write down the complex coefficient of those real part and the imaginary part, and we get it in the polar form, which comes out to be 10 volt with the angle of 53 degrees, 53.1 degrees. And same thing for the other impedance, Z2, and find out its amplitude and its angle. Okay, now at this point we can do the summation, which is determine the denominator of the equation and also the product, which is going to be the numerator. So when we figure those conversions, and it's going to be all in polar form because we want to do a division, and the division is much done easier in a polar form than in the rectangular combinations. So you get the total impedance in this case. So it is basically the same law as the electrical circuit applies here, except you have to work with a J coefficient as well as the real number. So here we have figure out the total impedance of the circuit, and if we know the voltage, which was 24 volts, we can divide that to get the current. Again, in this case, when you divide the two numbers in polar coordinates, you just divide the coefficients and then subtract the angles from each other to get, in this case, negative 13.7. For the current, because the negative 13.7 was in the denominator, it subtracts from 0 degrees, so it gets positive 13.7 degrees with the amplitude of 4.58 amps. Note that the circuit is a capacitive. Why? Because the current leads the voltage. Adding branch currents, if you have parallel circuit, and if you know the individual current in each branch, you just add the imaginary and real part to get the total current. You find out in the polar form, and if you know the voltage, then you can figure out the arctangent, and to get the rectangular form and come back into the polar form coefficients, and therefore you have it in both complex form and both in the polar coordinates. So if you have parallel circuit with three complex branches, the circuit which has more than two impedances in parallel basically uses this complex method of branch current, convert each branch impedance into the polar form, and convert individual branch currents from polar to the rectangular one, because you can add again to get the total current. Then convert the total current from rectangular to polar form, and the impedance of course can remain in the polar form with this magnitude and phase angle, or can be converted to the rectangular form for its resistive part and the reactive component. So this would be the procedure for all of this. So when you're adding them in the rectangular form. When you do the multiplication and division, you basically use the complex form.